We're talking about the 3-Eye Atlas. There are some new pictures that are revealing something really weird, which is baffling astronomers and also amateurs alike.
So here's the thing about comets. They're supposed to follow rules. Show up, put on a nice tail display, then quietly fade back into the cosmic void like a well-mannered party guest. But 3-Eye Atlas did not get this memo. Instead, 12 spacecraft across the solar system report the same shocking result. 3-Eye Atlas is still active, still outgassing, still breaking every rule we know. And the most dangerous phase may be just beginning, the comet that refuses to sleep. December 19th, 2025 was supposed to be the big finale. That was the day 3-Eye Atlas made its closest approach to Earth, a comfortable 170 million miles away, because apparently even ancient interstellar objects know about personal space. Astronomers had been tracking this cosmic wanderer for months as it swung around the sun and started its long goodbye back into the darkness between stars. The script was written. The comet would dim. Scientists would pack up their instruments. Everyone would go home satisfied with some nice data and a few pretty pictures for the textbooks. Yeah, about that. 8 days after closest approach, 12 different spacecraft across the entire solar system are all reporting the same thing. 3-Eye Atlas is still actively outgassing, still shedding material, still putting on a show that, by every model we have, should have ended weeks ago. It's the cosmic equivalent of a house guest who was supposed to leave Sunday, but is still on your couch on Wednesday, eating your food and showing no signs of slowing down. Europa Clipper, currently cruising toward Jupiter with presumably better things to do, turned its ultraviolet spectrograph toward the comet and detected oxygen and hydrogen still streaming off the nucleus. Not residual wisps, active outgassing. The Parker Solar Probe, which has been stalking this comet since October with the dedication of an ex who won't stop checking your Instagram, captured about 10 images every single day for weeks. Even now, as 3-Eye Atlas races away from the inner solar system, those instruments are picking up brightness that absolutely defies the expected fading curve. And oh, would you look at that? ESA's JUICE spacecraft, bound for Jupiter's moons, observed 3-Eye Atlas from 41 million miles away and found not one, but 2 distinct tails still extending from the coma. The full scientific data won't drop until February 2026 because the spacecraft is using its high-gain antenna as a heat shield during transit, which is the kind of improvised engineering decision that makes you realize space exploration is basically just very expensive MacGyvering. Here's where it gets genuinely wild. The James Webb Space Telescope, that $10 billion golden honeycomb we parked at L2, took a close look at what 3-Eye Atlas is made of, and what it found explains a lot while simultaneously raising about 15 new questions. Most comets run on water ice. It's their whole thing. As they approach the sun, that ice sublimates, fancy word for turns directly into gas without bothering to be liquid first, and creates the spectacular tails that have been freaking out humans since we first looked up and wondered what was happening. But here's the catch. Water ice only gets active at relatively close distances to the sun. Once you swing past perihelion and start heading outbound, that activity typically drops off like enthusiasm at a Monday morning meeting. 3-Eye Atlas is not a water comet. This thing has the highest carbon dioxide to water ratio ever observed in any comet. We're talking an 8-to-1 ratio of CO2 to H2O, 6 standard deviations above what scientists consider normal, which in statistics speak means so far outside the bell curve, it's not even in the same parking lot. Why does this matter? Carbon dioxide sublimates at much colder temperatures than water, which means 3-Eye Atlas can remain active far from the sun, in regions where ordinary water-driven comets would be inert chunks of ice and rock, just vibing in the cold, like everyone's co-worker who keeps the office thermostat at 62 degrees. The numbers are staggering. JWST detected carbon dioxide streaming off the nucleus at 129 kilograms per second. Water, a measly 6.6 kilograms per second. This isn't a water-driven comet. This is a carbon dioxide engine that apparently got the memo about eventually shutting off and decided that memo was more of a suggestion. The post-flyby checks confirmed full activity, confirming that comet is still very much alive. But what scientists discovered about where this comet actually came from would make everything even more extraordinary. 7 billion years in the making. Let's throw some numbers at you that should make your brain itch a little. 3I Atlas entered our solar system traveling at 137,000 miles per hour. By the time it reached perihelion on October the 29th, 2025, it had accelerated to 153,000 miles per hour. For context, the fastest human-made object ever, the Helios 2 probe, maxed out around 157,000 miles per hour. This random space rock is casually matching our best engineering achievements just by falling toward the sun. The technical term for its arrival speed is hyperbolic excess velocity. For 3I Atlas, that number is 58 kilometers per second, the highest of any known interstellar object. Translation: this thing absolutely, definitively, no questions asked, came from somewhere else. So where? Scientists traced the trajectory backward through time and space, and it points toward the thick disk of the Milky Way. That's a region populated by some of the oldest stars in the entire galaxy. The chemical signatures back this up. Carbon isotope ratios look similar to Earth's, but the cosmic radiation exposure is absolutely wild compared to anything that formed around our sun. Here's where it gets genuinely mind-bending. Current estimates put 3I Atlas somewhere between 7 and 14 billion years old. Our entire solar system, 4.6 billion years. This comet was ancient when our sun was still just a theoretical possibility floating around in a molecular cloud. The extreme CO2 enrichment tells us something specific. In any forming planetary system, there's a boundary called the carbon dioxide frost line. Beyond that line, temperatures stay cold enough for CO2 to remain frozen solid. 3I Atlas must have formed way out in the deep freeze of its home system, locking away carbon dioxide that stayed frozen for longer than most stars even exist, until about 6 months ago. For the first time in possibly 7 billion years, this ancient ice is experiencing the warmth of a star, and it's responding like someone who just discovered espresso after the longest nap in cosmic history. The Mars observations were particularly clutch. On October the 2nd, 2025, the Mars Reconnaissance Orbiter snapped images from just 19 million miles away. But the real hero was ESA's ExoMars Trace Gas Orbiter. Between October 1st and 7th, it tracked the comet so precisely that trajectory predictions improved by a factor of 10. Fun historical footnote: this was the first time ever that Mars orbiter data got accepted into the International Astronomical Union's Minor Planet Center database. We literally mapped an interstellar visitor using observations from another planet, just casually doing stuff that would have been science fiction when most of us were born. Even the Perseverance rover contributed observations from the surface of Mars. At that point, basically everyone with a camera wanted in on the action. The chemical fingerprints revealed an origin older than our solar system, but the physical structure of the comet was about to reveal something even stranger. The coma that keeps growing. The Hubble Space Telescope is pretty good at taking pictures. It's sort of the entire point. And when Hubble focused on 3I Atlas, it captured something that made a lot of astronomers do a slow blink. The coma, that fuzzy halo of gas and dust surrounding the nucleus, measured 26,400 by 24,700 kilometers. That's roughly twice the diameter of Earth, wrapped around a nucleus, probably less than 1 kilometer wide. Picture wrapping a grape in a fog bank the size of a major metropolitan area. Now, scale that up by a factor of about 26,000. Hubble calculated dust loss rates between 6 and 60 kilograms per second. Vigorous stuff, but the really weird part was watching the coma constantly change shape. Images captured a teardrop formation near perihelion that kept transforming over time. Jets appeared and vanished. Structures shifted around. The whole thing was shape-shifting in real time, like the comet couldn't decide what it wanted to look like. Then there's the polarization data. When scientists measured how light from the coma was polarized, they found extreme negative polarization signatures. This is unusual even compared to already unusual comets. It suggests the dust particles and surface materials have properties that don't match anything we've catalogued in our solar system. The coma wasn't just big, it was alive, constantly reshaping itself as different surface regions rotated into sunlight and started venting material into space. Imagine a spinning sprinkler system, except the sprinkler is the size of a small mountain, and it's been dormant for 7 billion years, and it's spraying ancient interstellar gas everywhere. And then came the X-rays, because apparently we weren't done being surprised. X-RISM conducted 17 hours of observation between November the 26th and 28th. What it captured was historic. The first ever X-ray image of an interstellar comet, carbon, nitrogen, and oxygen signatures in a halo extending 400,000 kilometers from the nucleus. Let's contextualize that distance for you. The Moon is about 384,000 kilometers from Earth. This comet was glowing in X-rays over a volume larger than the space between us and our own Moon. That's a lot of ancient material being shed by something smaller than most ski hills. The coma told one story, but the tails trailing behind the comet were about to reveal behavior that made astronomers question fundamental assumptions about how comets work. A tail pointing the wrong way. Okay, quick refresher on how comet tails work. Solar radiation and solar wind push dust and gas away from the sun. This is why comet tails always point away from our star, no matter which direction the comet itself is traveling. It's one of the most reliable rules in celestial mechanics. You can literally count on it. 3i Atlas looked at that rule and apparently decided it was more of a suggestion. Starting with Hubble observations in July 2025 and continuing through December, astronomers documented something that fundamentally should not exist: an anti-tail, material streaming toward the sun instead of away from it, directly contradicting the constant pressure that should be pushing everything backward. Okay then, that was always allowed, I guess. Multiple papers have attempted to explain this. One theory suggests ice fragments are being shed from the sun facing side of the nucleus, temporarily resisting radiation pressure before eventually getting swept back. Another proposes a debris swarm lagging behind due to non-gravitational acceleration effects. Everyone has ideas. Nobody has certainty. But wait, there's more. Observers detected wobbling jets within the tail structure. These weren't static features. They moved with a periodicity tied to the comet's rotation, sweeping back and forth like a cosmic lighthouse operated by someone who definitely had too much caffeine. The jets stretched tens of thousands of kilometers and persisted night after night. Both amateur astronomers and professionals recorded multiple tail features and these strange collimated jets. The tail wasn't just a passive dust trail getting shoved around by solar physics. It was an active structure being constantly fed from the nucleus. The anti-tail remains one of the most puzzling features of 3i Atlas. In a universe where comet tails follow predictable rules, this object showed up and started freestyling. The strange tail behavior hinted at forces acting on the comet from within, and measurements of its rotation were about to confirm that the nucleus itself was far from stable. A nucleus spinning faster. Alright, so we've got this ancient ice ball doing things it shouldn't be doing. Naturally, scientists wanted to understand what's happening at the surface level. What's actually driving all this chaos? Turns out the nucleus rotates with a period of roughly 15.5 to 16.2 hours. Scientists figured this out by tracking the wobbling jets and watching periodic brightness variations as different regions rotated into and out of view. Here's what that tells us. The comet isn't uniformly active everywhere. Specific patches are doing most of the heavy lifting. Active zones rotating into sunlight, triggering pulses of gas and dust release with clockwork regularity. Think of a pot with multiple holes in the lid, each one venting steam as it passes over the burner. Spectral data revealed something else interesting, a subtle reddening trend early in observations, suggesting organic compounds similar to what we see on solar system comets. But this reddening evolved over time as ongoing activity exposed fresh material beneath the weathered surface. Layers that hadn't seen starlight in literally billions of years were finally getting their moment in the sun. The rotation patterns and surface variation were way more complex than expected. This comet has internal structure. It has geography, active regions and dormant zones and transitional areas. It responds to solar heating in ways that reveal constant interaction between interior and surface. But here's where things get slightly ominous. Those jets aren't just pretty features for the astronomy photo album. Every gram of material blasted into space by sublimating ice acts like a tiny thruster firing. Newton's third law doesn't take vacation days, not even for interstellar visitors. The rotation revealed surface activity that refused to quit, but the real shock came when scientists measured what all that activity was doing to the comet's path through space. An orbit being rewritten. After perihelion, when 3I Atlas had swung around the Sun and started its outbound journey, orbital tracking teams noticed something off. The comet wasn't quite where calculations said it should be. Tiny deviations from predicted positions appeared in the data. The comet was being pushed by its own exhaust. This phenomenon is called non-gravitational acceleration. When material jets off a surface, it creates recoil thrust, tiny on any given day, but accumulating over weeks and months. For 3I Atlas, the combination of CO2-driven outgassing and directional jets was nudging the trajectory in ways pure gravity couldn't account for. Citizen scientists and professional networks noticed sudden brightness spikes near perihelion that blew past model predictions. These outbursts suggested either substantial new activity or enhanced surface events, pumping more material into space than anyone anticipated. Even after perihelion, the comet didn't just coast on its gravitational trajectory. It kept reacting dynamically as jets persisted. Orbital solutions required constant updates. Every time scientists thought they'd nailed down the path, the comet did something slightly unexpected. The ExoMars data proved essential here. By improving trajectory predictions tenfold, Mars observations gave scientists a baseline precise enough to detect these subtle deviations. We were literally watching an interstellar object rewrite its own orbit in real time. The forces reshaping the orbit were also stressing the comet itself, and scientists began watching for signs that this ancient traveler might not survive its passage through our solar system intact. An ancient traveler under strain. Let's zoom out and inventory everything we know about 3I Atlas. Unusual brightness refusing to fade on schedule. CO2, rich composition driving activity where water comets would be dormant. Extreme polarization signatures, suggesting exotic dust properties. Wobbling jets, maintaining impossible anti-tail structures. Non-gravitational acceleration, actively rewriting the orbit. Each data point contributes to a picture of an object experiencing something it hasn't experienced in a very, very, very long time. For 7 billion years, possibly longer, 3I Atlas drifted through the cold emptiness between stars. Its volatile ices stayed frozen. Its surface stayed unchanged. Whatever processes shaped it around its parent star remained locked in suspended animation across timescales that make human history look like a brief sneeze. Then it tumbled into our solar system. The intense solar heating is activating compounds that may not have sublimated since before our planet existed. This comet is shedding material that predates most of the stars visible in the night sky, and the process is clearly stressing the object in measurable ways. The internal structure is being reshaped kilometer by kilometer. Jets are carving new surface features. Volatile reservoirs are venting to space. The rotation itself may be changing as mass loss affects the comet's moment of inertia. How long can this continue? Honestly, nobody knows. 1I/Oumuamua showed zero cometary activity and passed through silently like a ghost. 2I/Borisov was active, but we observed it with far fewer resources. 3I Atlas is putting on the most detailed performance from an interstellar visitor we've ever witnessed, and it's doing so while clearly under physical strain. There's a countdown happening. The comet is heading toward a Jupiter flyby on March 16, 2026, passing within 36 million miles. After that encounter, it accelerates even faster and begins permanent departure from our solar system. The Juno spacecraft might observe during the flyby, fuel permitting. Ground telescopes will track 3I Atlas through spring 2026 as it fades in the pre-dawn sky. Then it's gone, forever. Breakthrough. LISTEN pointed the Green Bank telescope at 3I Atlas on December 18th, searching for techno-signatures, any trace of artificial signals. Avi Loeb had floated speculation about non-natural origins back in July, which the astronomical community mostly received with polite eye-rolling. The search found nothing unusual. NASA's Amit Kshatriya stated flatly that it looks like a comet, behaves like a comet, and all evidence says it's a comet. But the fact that we even checked tells you something about how genuinely strange this visitor has been. The data collected will take years to fully process. Papers will proliferate. Models will get revised. Textbooks will need updates. Every future interstellar object will be compared against what 3I Atlas taught us. What this visitor looks like as it fades into darkness beyond our solar system may permanently change how we understand interstellar objects. And somewhere out there, more of them are already falling toward us. If this comet is still active after passing Earth, what do you think it means for what's coming next? Share your thoughts in the comments.